Hello everybody, this is video 3.4, looking at fraction, addition, and subtraction. So let's start with a problem like 4/5 plus 3/4. And we could draw a picture of 4/5. And so here's a bar broken into fifths, and then we'll do 3/4, and we'll try to use about the same length bar here. Let's get rid of that. So 1, 2, 3, 4. So we've got 4/5. So we're going to trade in 4 of the 5 plus 3/4. So if we were to add all of these pieces together, what would we get? Well, we know it's going to be more than 1, and because this piece right here is going to more than fill up this gap right here. So we know it's going to be more than 1, and we know it's going to be less than 2 because we're missing this much and we're missing this much. But as far as the exact amount goes, given this model, it's going to be really hard to tell. Now, as you would probably imagine, the really common incorrect answer to this is going to be, well, we've got 1, 2, 3, 4, 5, 6, 7, 7 pieces, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9. This is going to be the most common incorrect answer you're going to see. It also is going to be common because students are going to line this up like this and then just add 3 plus 4 makes 7, and then 5 plus 4 makes 9. And this is not correct, right? And you should be able to think about how you're going to explain to students that this doesn't work, other than just to say, that's just not how we do it. So if you think about our definition of fractions, the key word that we kept saying over and over that you really have to reinforce is equal size pieces. If we don't have equal size pieces, then none of this is going to work. And so this 9 has to be in equal size pieces. And so as soon as a student tries to add these two fractions together this way, you need to be able to tell them immediately, directly, well, the 9 pieces aren't the same size, so we can't add like that. Or the 7 pieces that you have are not all the same size, so that fraction doesn't work either. So however you want to address it, this is your key idea that we're talking about equal size pieces. So to do the addition, we're going to need to have equal size pieces. So if we go back to our original problem, 4/5 and 3/4. As I mentioned in a previous video, for right now, we're going to try to work with mostly problems where your common denominator we're just going to get by doing the product. Now, if you already know how to find the least common denominator, then you know in this case it's going to be the same thing. It's also going to be 20. But we're going to use our idea of equivalent fractions from the previous class. And so we know that my common denominator is going to be 20. So I got to break this thing into pieces of 20. And so then this is going to be broken into 4 pieces. And so then this also gets broken into 4. And we could draw, if we want, a model for this. And so we want this much. This is my 4/5. But now we can break each of these pieces into 4. And so now I know that this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And so this is also going to be 16/20. So I can use a model to reinforce this. We also looked at that area model where we took a rectangle and we broke it into fourths one way and then fifths the other way. And so we saw that we had 20ths. So I mean, we could use either model that we want. So fifths, and now we're going to break that into fourths. And so we could see that our our 4/5 here is also going to make 16/20. So whichever model it is that you need to use, make sure you have at least one. Again, the more models that you have, the better you're going to be able to explain this. If you just have the one model and you explain that, you use that for students, and they kind of look at you like, they don't know what you mean, and that's all you have to go to, then you're kind of stuck. So either way works. We do the same thing with the 3/4 by the same reasoning, by 5 and by 5. So this makes 15, and so we get 31/20. Excuse me. So this is going to be our answer, this 31/20. And as we estimated earlier, it's more than a whole because it's more than 20/20, but it's less than 2 because it's not quite to 40/20. But this would be our solution. Again, this is the key idea, that we need the pieces to all be the same size. So once I break this into 20ths, then the problem makes a lot more sense. 16 and 15 of the same size makes 31 of the same size. And what size is it? It's the 20. Now, again, once we reinforce this idea that it's the same size pieces, then this gets us around another really common mistake, and that's 31/40, where now they're going to add the 15 and the 16 to get the 31, but still want to add the 20 and the 20 to get the 40. And so you should be able to explain why this isn't 40, because the size of the pieces hasn't changed. So at the end there, we got 31/20. And so we can also convert this into a mixed number. So hopefully you remember that this is an improper fraction. And so we can convert this into a mixed number, which is an integer with a proper fraction. Now I have to look into this because I'm not sure if you have an integer with an improper fraction, what that would be called. But this was the definition that I found, that is an integer with a proper fraction. And we can get into a little bit more of this a little bit later on. We start talking about division and fractions, because really this is all about division. But we could talk about this in terms of just our definition of a fraction by using our number line. Ooh, that should be, there you go. So we could draw our number line and see that this is going to make a whole. So this 20/20 makes a whole. And so then this amount is an extra 11/20. So we could use our number line to sort of model the division without saying anything about division. I'm sure for a lot of you, just divide the 31 by 20. How many times does it go in? What's the quotient? What's the remainder? But if we haven't done anything with division yet, we don't want to use those terms because they're not really defined yet. And we don't want to conflate fraction work with division work. We can do all of this thinking about it just in terms of models and definitions of fractions. So we know that it makes one whole on our number line, and then there's 11/20 left over. So this is my integer. This is my integer value, and this is my fractional value. If you're curious, the symbol for a fraction is a little q with another little line. But specifically it needs to be a proper fraction. There you go. Mixed number. Okay, we didn't mention this before, and I'm not sure why, if it wasn't in my notes or if I just didn't see it in the book. But we can also talk about finite decimals and fractions. And so this is kind of a short section, so I'm going to kind of squeeze this in here. So you may have noticed in the past that some fractions, like 1.3, or I'm sorry, like 1/3, give us a decimal that repeats. And that's what this little bar represents, that some amount of this will repeat. And that bar could be over 2 3s, could be over 1 3. I mean, this is a bunch of 3s. So it's just going to keep going. So whether you think of it as 2 3s repeating, or 1 3 repeating, or 4 3s repeating, it doesn't make a difference. It's an infinite number of 3s. So this is going to keep going. And some will have a different part. Uh, so you may have something like 1/6 where you have 0.16666 repeating. And so you have a number that's different, like this 1, and then you have a different number like this 6 that repeats. You even have kind of weird things like 1/7, where you have 142,857, where you have this 6 number block that repeats. So this 1/7 is going to keep repeating 142,857, 142,857, 142,857. It's going to keep repeating that 6-digit block. But the point is that all of these are infinite, and they're just going to keep going. Now, compare this to fractions that are finite or terminating. And so a really obvious one would be 1/2. It's just 0.5, and then it stops. There's no repeating. Now, there's probably at least one person thinking, well, there's a repeating 0. Yeah, but it doesn't hold value, so we're not going to worry about a repeating 0. We're talking about a repeating value that has value. So this 0.5 terminates. It stops. 1/4, 0.25. It stops. 1/8. Oh, let's use something different than 1. So 3/8, 0.375, and it stops. So these are all finite or terminating. Now, to clue you in, and this is pretty much entirely optional, if your denominator is only the product of 2's and 5's, then it'll terminate. Once your denominator is divisible by something that's not a 2 or a 5, like a 3 or a 7, then it's going to keep repeating. So if you're in a position to where you're working with students and you want them to work with something that absolutely terminates, so like 1/5 is 0.2, these all terminate. So just use some number of 2's and 5's, multiply them together, and use that as a denominator. And it doesn't matter what the numerator is, it will be a terminating decimal. The reason for this we don't need to get into, and like I said, this is all this 2's and 5's thing in terminating decimals is optional, but it's kind of handy. The point is that for finite decimals, we can do an expanded form using fractional place values. It's a little bit harder to do with infinite because the expanded form would just keep going. We'd have a dot, dot, dot. And you could, but for right now, just really kind of focus on these finite decimals. So this 0.5 would be 5/10, or this 3.375 would be 3/10 plus 7/100 plus 5/1000. And so we can get an expanded form out of that. And if we had a mixed number, like say 6 3/8, well, we'll do this up here, 6 3/8, we could do it as the normal 6, 3/10, 7/100, 5/1000. So we could put the integer part, do the expanded form on that, and expand that out. If it were 16, we could do 10 plus 6 plus blah, 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 blah. So this allows us to do expanded form using the place values for decimal places as well. All right, so kind of a short section. Your checkpoint problem, I want you to think about this problem. And I want you to think about what this represents. And so this could be maybe something that a student would draw, or maybe a picture that you would accidentally draw in class. And I'm saying accidentally because maybe you don't mean to draw it this way. But I want you to think about, like, what do you think this problem represents? What problem do you think you're trying to ask or is being modeled here? What do you think it models well? And what do you think maybe it doesn't model as well? So we can talk about this in office hours, or we can talk about it in class. If you have any questions, please let me know. All right, thanks.